Hello again and welcome to this lecture on mechanical design. In this lecture I'm going to talk about bending of beams. We discussed in the previous lecture some simple ideas about beam bending, so I'd like to build on those, again introduce the basic equations for beam curvature and the corresponding equations for the shear force and for the loading in relationship to the moment. And then we will again rederive the equation for deflection, which is actually the basis of what we want to do. And the application for design is to control the level of deflection to be below a certain amount. So that would be explored in one of the examples, and also to control the angle of deflection at the supports. Let's say if we have bearings, then we'd want to reduce the angle of deflection at these bearings. All of these things will be useful when we come to design application in the future. So for now, I will start from the beginning, just laying out the equations and discuss with you the various methods for calculations of deflections. And we will see that we're going to focus on one particular method that is useful and easy to use. And then we'll follow that with a couple of examples. So let's start at this point where we can write equation for the beam curvature, and the equation for the beam curvature, as we know, it is 1 over rho is equal to kappa, and kappa is the curvature of the beam, which is now approximately equal to d2y by dx squared. And as we have seen, the kinematics, assuming that the beam curves in a circular path, then the curvature is directly proportional to the applied moment divided by the flexural rigidity. So that's kind of the basic kinematic equation that we have here. And then what we will see is that since we have V, which is the vertical shear force, is equal to the change of moment with respect to x, therefore we would have V as equal to y triple prime. Y triple prime is differentiating y 3 times with respect to x. And then we would have Q as equal to dV by dx. And notice that Q positive is up in here, and shear is positive is up on our coordinate system. Then we would have Q is equal to y, now four derivatives of y itself. Notice that dm by dx, we will have basically to note that ei, if we take it to the other side here, then m will be equal to ei times y double prime. And thus, if we take the first derivative of m, then you have to introduce e times I here and introduce e times I here. So these are the basic equations. It means that given q as a function of x, then we take one integration, we get v as a function of x, and then we take another integration, we get m as a function of x, we take another integration, we get the slope as a function of x, and then we take another integration, we get y as a function of x. So it's kind of a long process starting from q, and that can be done in 2 steps. One step is that we can focus on finding the moment as a function of x from simple equilibrium, and once we find the moment, then we integrate it twice, going this way to find the slope and to find the deflection. Or we can start from q all the way and proceed to finding y as a function of x. So these are the two possibilities here, and what I'll do now is I'm going to give an example, and in this example we will discuss very simple beam deflection from the construction of the shear and the moment diagram and the shear force diagram. So we can actually use these diagrams and construct the deflection curve. Now this is going to be the simplest possible example of a simply loaded beam, and if we go to a more complex distribution of loadings, it would be easier if we have a systematic method. So I'm going to explain this simple example first to show you how to think about building a deflection curve graphically. And then once we do that, then we go into the math and discuss the various possibilities for calculations of the deflection in another example. So in this example, we have a simply loaded beam, and the simply loaded beam is having a load W that is going into the negative direction. So the load is 80 pound force per inch, and the reactions, of course, once if we multiply W times L, it gives us a total force on this beam here, and the total force, we split it half in here and half in here. We got the reactions very quickly. So the reactions will be WL over 2 on the two sides. Now that is this diagram here is actually the force diagram. So from the force diagram, we usually compute the shear force diagram, and the shear force diagram, we start from the left side. We have a concentrated force of WL over 2, and that will be basically V0. So V0 here is WL over 2. And then as we move to the right for x positive, then we have to add this negative force, because remember W up is positive. So if we have now the load is going downward in the negative y direction, then the integration of the uniform load is a straight line, and therefore we can create a straight line from the uniform load by knowing that we start from V0, which is WL over 2, and then as we have W, so the integration of up to this point here, half of the beam is W times L over 2, and when you add W times L over 2 to negative to positive WL over 2, you get 0. So the slope will decrease, the straight line will decrease until it hits 0, and we would still keep adding this part of the distribution of the load, which is again negative. The integration of a uniform load is a straight line, and again it reaches the value of V1, which is minus 800 pound force. So we have reached now an understanding of how to find the shear force diagram. So the bending moment diagram is another integration. So going from here to here is integration. Integration is the area under the curve. So every point here will have the corresponding area under the curve. So if I consider a point here, then I would go and I have to find this area here, and that would be the area, would be the value of the moment here. So as I mentioned, there is the scaling factor is EI, so we have to put the EI in the bottom here. So you start from Q over EI, then you construct V over EI, and you construct M over EI, and the construction here is a straight line. Then the corresponding integration is a parabola. So you have a parabola, and the maximum of the parabola is exactly in the middle, and the value of the moment at the left side is 0, and then it increases as we accumulate area under the curve. So this is the area under this curve here. Let me just clear this page to show you. So if I have this triangle here, and I calculate the area of the triangle, it will be half times V0 times L, and V0 is 800, so it would be half of 800 would be 400, and L is 20, so it would be 400 times 20, and 400 times 20 would be 8,000, and that is basically the height right here. Would be that value here. Okay, so just integration. Next step is to obtain the slope diagram, and the slope diagram is one more step of integration. Again, integration here. Then we know that the slope of the beam in the middle here is the slope. This is the deflection curve. We know that the slope of the beam in the middle is equal to 0, so the angle is going to be equal to 0, and therefore we would have to start from a value that is equal to the area under the parabola here, this parabola here, on the left side. So therefore EI theta 0 will be the area under this part of the parabola, and then it will build up to 0 and it continue here. So this is a cubic here. And then one more integration, we get the deflection curve EI, and the deflection curve, as you can see here, this will be a function of x. This is quartic value. So this is all the what is involved in finding the deflection graphically. So as you can see, it's a little bit depends on common sense and experience, but now we're going to do the same job using mathematics immediately, as we will see here. So what I will do is I'm going to write an equation for the moment, and then divide it by EI, and then integrate it once to get the slope. I'm going to have a constant of integration, integrate it twice to get the deflection curve, and I'm going to have a second constant. I will find the two constants of integration applying the boundary conditions. So here is the procedure. So I have here this equation for a moment. It's composed of two parts. One is a result of the reaction on the left. So let's say if I'm at any point x here, at this point, so let's say x is right here. So x is right here. Then I will have the reaction WL over 2 times x, because it will create a moment here, this reaction. And then I will have half of this, like this force here, I can concentrate it halfway, and it gives me an opposite moment at this point. So this is the moment due to reaction. This is the moment due to the uniform loading when it's concentrated at x over 2. So BWx is the total load, and then you multiply by x over 2, you get the moment. Very simple. Then I divide by EI, and then do integration. So if I have the integration of m dx, will be EI times dy by dx, and the integration gives me a constant C1. Notice that dy by dx is theta, so I can use some condition here that theta is equal to 0 midway at L over 2 and determine C1, but I'm going to leave it until the end and determine C1 and C2 together. So if I integrate one more time, then I get EI times y. It will have C1 times x and then C2, and the deflection y is equal to 0 at x equals 0. That gives me C2 equals 0 directly, because everything here, when x is equal to 0, all of these three terms will be equal to 0. And then to get C1, I just apply the second condition that the deflection at x equals L is also 0, and that's all for C1, and gives me the value of C1. Having done that, I can plug these back, and I find the y as a function of x. You can see that it is fourth order equation, because x here multiplied by x squared, this is a cubic, another one multiplied by x cubed gives you fourth order. So it's a fourth order equation. And then the slope theta is a cubic equation, so it has the highest order is cubic. And we can test things now to find the slope at x equals 0. Substitute x equals 0. We get the slope equals minus WL cubed over 24 EI. And at x equals L, we get positive WL over EI. So we have determined all of these values, and then finally we determine the value of the maximum deflection. As you can see here, the maximum deflection is exactly in the center, and when dy by dx is equal to 0, we get the maximum deflection, and therefore we obtain minus 5 WL to the power 4 over 384 EI. So that's the same as in Shigley's table A97, using mathematics to do the integration. So it's a pretty straightforward integration process if we had a simple loading. So in the next, what we will see is that there are systematic methods to calculate the deflections. So in the next lecture, we will discuss those, and then we will also have another lecture, maybe one lecture on a systematic method to do the deflections using what we call singularity functions, and then I'm going to have another final lecture on the deflections using a numerical method, which is the finite element method. So let's stop here, and we will pick up in the next time. So we'll see you later.